Hi everyone. In this lecture video, I'll be doing properties of conjugate and modulus followed by questions on this topic. So the first property that you are going to write is based on say conjugate. So if Z is A plus IB, so we know that Z bar is defined as A minus IB. So if you again take conjugate of this conjugate, again we have to write I as minus I, it would become A plus IB, which is giving you Z. So the property is Z bar whole bar is always equal to Z. This is the first property for conjugate. And the second property is Z1 plus Z2. If you add two complex numbers and take conjugate or find their conjugates and add, the result would be the same. Then the third property is if you multiply two complex numbers, take the conjugate of the resulting complex number or find their individual conjugates and multiply, it would be the same. This is property 3. Then coming to property 4, if you write Z1 by Z2 whole conjugate, divide two complex numbers and take conjugate or take the conjugates and divide, the result would be the same. This is property number 4. So these are purely based on conjugate, but we'll also have some properties where we'll mix up modulus and conjugate. So now, suppose we have Z as A plus IB again. We know that modulus of Z is defined as root of A square plus B square. So we can say that mod Z, mod of minus Z, mod of Z bar, mod of minus Z bar, all will have same modulus. Each will be equal to root of A square plus B square. All this will be the same. So now you can say when you add two complex numbers, take conjugate of this or just write mod of Z1 plus Z2, they will be same only. And that is also equal to mod of Z1 conjugate plus Z2 conjugate. So the modulus will be same for all of them. The same thing will also hold for minus. So you can put a minus also here. And if I write mod of Z1, Z2 conjugate, this is same as mod of Z1 conjugate into Z2 conjugate. And you can also write mod of Z1 conjugate into mod of Z2 conjugate. You can split like this in modulus, and that is same as mod Z1 into mod Z2 or mod of Z1, Z2. So whether you write mod Z1, Z2 or mod of Z1, Z2 conjugate, it is same. Similarly, you divide them, take conjugate and mod of that. That would be equal to mod of Z1 by Z2 itself. Okay, so the ninth property, I'll just write mod of Z1 into Z2 into Z3 up to Zn. You can write mod Z1 into mod Z2. That is, you can find individual modulus and multiply. That is, whether you multiply all of them and take mod of the resulting complex number or take individual mods and multiply, the result would be the same. So based on this, if I have to write something like modulus of Z power n, then this is mod of Z into Z into Z like this n times. And according to the previous property, you can write this as mod Z into mod Z into mod Z, so on n times. So we can therefore write this as mod Z whole power n. This is property number 10. So modulus of Z power n is same as mod Z whole power n. Then coming to the 11th property. So if Z is A plus IB, you know that real part of Z will be A. That is less than or equal to root of A square. Obviously, if I add B square, it will be lesser than that. And root of A square plus B square is actually mod Z. So we can say real part of Z is less than or equal to mod Z. Some inequality questions can be solved using this. Similarly, when you write imaginary part of Z, it is B. And you know that that is less than or equal to root of B square. Obviously, you add something like A square, it is still valid. So which is nothing but mod Z again. So imaginary part of Z also less than or equal to mod Z. Even this is useful in solving some inequality questions. Then coming to the 12th property. So whenever you have modulus of Z1 plus Z2 whole square, how to expand this? So before we do this, you need another property. I'll write that first. Whenever you multiply Z and Z bar, that is A plus IB, multiplied with the conjugate A minus IB, this will give us A square minus I square B square. Now writing I square as minus 1, it would reduce to A square plus B square. But you know that if root is there, it is mod Z. So it is without the root, so it is mod Z whole square. So this is the most important property under this topic. Z bar is mod Z whole square. We'll be using this in a lot of problems. So this you need to by heart. Now, based on this only, if I consider mod of Z1 plus Z2 whole square, you can actually write it as the complex number Z1 plus Z2 multiplied by the conjugate of that. And as I told you, whether you take whole conjugate or individual conjugate and add, it would be the same. So you can write this as Z1 conjugate plus Z2 conjugate. Now multiply these two. Z1 multiplied with Z1 conjugate will be Z1 Z1 bar, which is mod Z1 whole square. Then you'll get Z1 Z2 bar plus Z2 Z1 bar plus Z2 into Z2 bar is mod Z2 whole square. So this can be written as mod Z1 whole square will write as it is, mod Z2 whole square also will write as it is. And now you see the next part, these two together can be represented in some notation. Let us look at that. Z1 Z2 bar plus Z2 Z1 bar. What is this? So basically you can say that it is mod Z1 square plus mod Z2 square plus 2 times real part of one of those complex numbers. Why? Because Z1 Z2 bar, if I consider as some W, for example, the conjugate W bar for this would be, you take the conjugate, Z1 will have a conjugate as Z1 bar, Z2 conjugate, whole conjugate will become Z2. So clearly you can see that one of them is the conjugate of the other, and you know that whenever you add a complex number conjugate, you'll get 2 times real part of that, 2 times real part of W. Or you can also write 2 times real part of W bar, because they'll have same real part. A complex number and conjugate have same real part, but they'll differ in their imaginary part by a sign. So I can just write 2 times real part of any one of them. So I can just write Z1 Z2 bar, or else I can also write this as mod Z1 square plus mod Z2 square plus 2 times real part of Z1 bar into Z2. So these two are the formulas. But apart from this, there is one more formula that we can write. This is mostly used in questions instead of these two. So you can write R1 square plus R2 square plus 2 R1 R2 cos of theta 1 minus theta 2. This is another way of writing the same formula, where if Z1 is R1 into cos theta 1 plus I sin theta 1 is the complex number in Euler's form or polar form. R1 is the modulus, so that's why this is R1 square. Similarly, if Z2 is R2 into cos theta 2 plus I sin theta 2, mod Z2 is R2, so therefore we got R2 square. And when you multiply Z1 bar with Z2 and look at it, that value will reduce to this notation. That is, you just have to write the real part of that multiplication. Like what is this? R1 e power I theta 1 and this is R2 e power I theta 2. So when I multiply something like Z1 Z2 bar, R1 e power I theta 1 will write as it is. Z2 bar would be R2 into conjugate would involve a minus sign here. So when you multiply, it will become R1 R2 e power I times theta 1 minus theta 2. So that is why, what is e power I theta again? Cos theta plus I sin theta. The real part would be R1 R2 cos of theta 1 minus theta 2. That is why I wrote this formula here, this part or this part. So this is the most important formula again in this topic. You have to remember this. Instead of these two, we mostly use this in problems. Similarly, this was for plus. If I have a formula for minus, then without deriving, I'll directly write. You can write this as mod Z1 square plus mod Z2 square minus 2 times real part of Z1 into Z2 conjugate. Or else you can write mod Z1 square plus mod Z2 square minus 2 times real part of Z1 conjugate into Z2. If you want to write in R theta notation, this is R1 square plus R2 square minus 2 R1 R2 cos of theta 1 minus theta 2. This is how you write mod of Z1 minus Z2 whole square. Now, if you add these two, mod Z1 plus Z2 whole square plus mod Z1 minus Z2 whole square, this cos theta term will cancel in both and you'll get the result as 2 times R1 square plus R2 square. That is 2 times mod of Z1 whole square plus mod of Z2 whole square. And in case you subtract them, mod of Z1 plus Z2 whole square minus modulus of Z1 minus Z2 whole square, you are going to get R1 square, R2 square cancelled out. You'll get 4 R1, R2 cos of theta 1 minus theta 2. This result also can be remembered. Sometimes for Z1 and Z2, they'll give a coefficient. In that case, we should see how to expand. So 17th one, I'll just write, if it is AZ1 plus or minus BZ2 whole square, where A and B are some real numbers, you can write A square R1 square plus B square R2 square plus or minus. If there is plus, you'll take plus. If there is minus, you'll take minus. 2AB R1 R2 cos of theta 1 minus theta. So this is what you are supposed to write. If some A and B are real numbers here, you can expand it like this. So it is nothing but extension of the previous properties only. If some number is there before Z1 and Z2, we use this. So for plus here, we use plus. For minus here, we'll use minus. And R1 and R2, what are they here? The same thing what I mentioned here. The same thing you have to use there. So this is the concept for properties of modulus and conjugate. We can start off with the problems. So here we have an equation in Z given and you need to find mod Z. So for that, we'll try to factorize it. So let us write down iz cube grouped with minus z and z square grouped with I. Then in this term, we can take iz common, then we'll have z square left out minus. Since z is already taken common, this minus sign is nothing but I square. I square is minus 1. So one I is already taken out, you can write plus I. Second one is 1 into z square plus I. From both the terms, if you take z square plus I common, you'll get z square plus I into iz plus 1 is equal to 0. And when the product of these factors is 0, either you can take z square plus I 0 or iz plus 1 equal to 0. Now considering z square equal to minus I as the first one, and second one gives you z equal to minus 1 by I, let us find out the modulus. So if you take mod on both sides, mod of z square equal to mod of minus I here. And we have a property that mod of z power n is mod z whole power n. We wrote this property already. Using this property, you can write this as mod z whole square equal to modulus of minus I will be 1. So from here, you can say mod z would be 1 because you can't write minus 1 for magnitude. You don't take plus or minus, take only plus. Similarly, here to simplify, you multiply and divide with I here. Then denominator is I into I square minus 1, which will cancel with this minus and give you I. If z is I, mod z will be 1. So in either case, modulus of z is 1 only. So we can therefore mark option D as the answer. So this was quite simple. Let's move on to the next question. So here we have mod z1, mod z2, mod z3 equal. If z1 plus z2 plus z3 is 0, what is the area of triangle formed by the points? Now, first thing that you can see is when mod z1, mod z2, mod z3 are equal, basically modulus of a complex number is distance from origin. That means all the three complex numbers are equidistant from origin. So if all are equidistant, the point equidistant from 3 points is the circumcenter of triangle. So basically you draw a triangle ABC. We know that circumcenter is equidistant from vertices. So if you represent Z1, Z2, Z3 as the three vertices of this triangle, the circumcenter of the triangle is origin. All are at same distance 1. So you can see that clearly circumcenter is origin. Circumcenter is origin, the radius is 1. Now, what is the centroid of the triangle? Basically, you have to add the three vertices and divide by 3. But they gave Z1 plus Z2 plus Z3 is 0, which means G is origin. And when can circumcenter and centroid coincide? Only for equilateral triangle. So therefore, you can say triangle is equilateral. Triangle ABC is equilateral. And once you conclude it is an equilateral triangle, now let's see how to find out area of this equilateral triangle. So if I have to find out the area of this equilateral triangle, you know that this is 30, 30. So write 30 here. And you can just write, drop a perpendicular here. And this will be bisected. The side will be bisected, a by 2, a by 2. So let us find the value of a. Like from this triangle OMB, sine 30 is a by 2 by 1. So we can write the value of sine 30 degrees as a by 2 by 1. And you will get the value of a as 2 into sine 30. And sine 30 is half, so 2 into half. So that is 1. And what is the formula for area of equilateral triangle? Root 3 by 4 into side square. So root 3 by 4 into 1 square you can write, and therefore you get the answer as root 3 by 4. And since it's area, it will be some square units. So root 3 by 4 square units means you can write option B. But let me just check the length of the side once. So the total angle was 60. This is 30. So sine 30, I wrote it wrong. I had to write cos 30 there actually. That's why it was different. This was cos 30 because I used adjacent actually. So there is a problem with that. Let me change it. So cos 30 degrees I wrote instead of sine 30, it was cos 30 because I took adjacent. So a by 2 is cos 30 is root 3 by 2. So a is root 3. That means the area of this triangle would be equal to root 3 by 4 into side square. That is root 3 square. That is 3 root 3 by 4 square units. So the answer would be 3 root 3 by 4 square units. So first option is the answer, not the second one. Okay. Now let's move on to the next question. What is the number of solutions of the equation z cube plus z bar is equal to 0? So usually when they give an equation in z and z bar, ask for number of solutions. The method is first you have to convert z bar in terms of z. For that, what you have to do is you have to apply modulus on both sides. That is, first you should write z cube equal to minus z bar. Apply mod on both sides. Mod of z power 3 is mod of minus z bar. And we have a property that mod of z power n is mod z whole power n. So write mod z whole cube. And this modulus of z bar minus z bar will be same as mod z only, right? Mod z. So when you simplify, you'll be getting mod z is equal to whole into mod z whole square minus 1 equal to 0, taking mod z common. So mod z equal to 0 or mod z equal to 1. Negative value is not allowed for modulus because modulus is distance from origin. It can't be negative. But when will mod z become 0? Only when z is 0. This is one of the solutions. And mod z is 1 is same as saying z bar is equal to mod z whole square, which is 1. Because mod z is 1, mod z square is also 1 square, which is 1 only. So z bar is 1 gives you z bar equal to 1 by z. And once you know that z bar is same as 1 by z, z bar is same as 1 by z. In the equation given z cube plus z bar equal to 0, we can also write z cube plus 1 by z equal to 0, which will give you z power 4 plus 1 equal to 0. That means this is going to have 4 solutions. Fourth degree equation will give 4 solutions. And z equal to 0 is another 1 solution. So that means together, how many solutions are there total? The given equation has 5 solutions. So the number of solutions of the equation is therefore 5. So option D is the right answer to this. Let's move on to the next question. If Z1, Z2, Z3 are 3 distinct complex numbers and A, B, C are positive numbers satisfying this criteria, what is the value of this? So first thing that you need to do is we'll write A by mod of Z2 minus Z3 equal to B by mod of Z3 minus Z1 equal to C by mod of Z1 minus Z2 is given. So let us assume this is equal, all are equal quantities. Either you can take this as K or you can take it as K after squaring. So I'll square this result because in the value that you wanted in the answer, you have a square. So I'll square them and equate with some K. Then you can clearly see that this can be written as A square by, suppose if I equate the first one with K, then I can write mod of Z2 minus Z3 whole square is equal to K. So from here you can write A square by mod of Z2 minus Z3 whole square can be written as Z2 minus Z3 into the conjugate of that equal to K square, because you know have a property that ZZ bar is mod Z whole square. So mod Z whole square can also be written as ZZ bar format. And since you wanted A square by Z2 minus Z3, you bring this term to right hand side. So that will give you A square by Z2 minus Z3 is equal to K square into Z2 bar minus Z3 bar. Similarly, instead of equating first one with the last one, equate second with the last or third with the last. You'll be able to get the result B square by Z3 minus Z1 equal to K square into Z3 bar minus Z1 bar. So this is equation 1, this is equation 2. Similarly, you will get C square by Z1 minus Z2 equal to K square into Z1 bar minus Z2 bar. By equating the last one with K, like by equating first with K, I got some result in the similar way. By equating second with K, third with K, whatever result I'm going to get, I wrote that directly, then add all of them. So when you add all of them, clearly the right hand side K square is common, rest of them will add to 0. So you can just say A square by Z2 minus Z3 is in cyclic order. B square by this ends at Z3, this starts at Z3, Z3 minus Z1. And next one starts at Z1, Z1 minus Z2, this sum will be equal to 0. So now when you look at the options, clearly the answer is first option 0. Now let's move on to the next question again. This is also based on the property that ZZ bar is mod Z whole square. This will use, and we may use some more properties. So modulus is given. You want to find the absolute value of this. Absolute value means modulus of that. 8 Z2 Z3 plus 27 Z3 Z1 plus 64 Z1 Z2. So what I'll do is, since mod Z1, mod Z2, mod Z3 are known, inside we'll take Z1, Z2, Z3 common. Then we'll be left out with 8 by the missing term is Z1. Second one missing term is Z2, 27 by Z2. Third one missing term is Z3, 64 by Z3. So this is same as whenever you have mod of multiplication, you can write individual modulus, mod Z1, mod Z2, mod Z3 into mod of 8 by Z1 plus 27 by Z2 plus 64 by Z3. Now mod Z1, mod Z2, mod Z3 are already known for us. They are 2, 3 and 4. Let us write that. So we'll write 2 into 3 into 4. Now for rest of the values, what we can write, we'll see. So we have 8 here. Mod Z1 is 2. When mod Z1 is 2, what is Z1, Z1 bar? Mod Z1 whole square, so 4. Mod Z2 is 3 means Z2, Z2 bar is mod Z2 whole square, which is 9. Z3, Z3 bar is mod Z3 whole square, 16. So you can clearly see 4 by Z1 is Z1 bar. So I'll write here This 8 by Z1 is nothing but 2 into 4 by Z1. Similarly, you have 27 by Z2 and you have 9 by Z2 is Z2 bar. So I'll write 3 into 9 by Z2. And the last one, if you see, it is given as 64 by Z3 and Z3 is 16 by Z3 bar. So 4 into, I'll write 16 by Z3 here. And you can write this as 24 into 2 times Z1 bar plus 3 times Z2 bar plus 4 times Z3 bar. This is with the help of the results which I wrote here, I concluded. And once you get this, you see here, this can be written as 24 into, inside the modulus, even if you write the complex number without conjugate, the modulus will not get affected. So let us write this. And this value is already given to us as 4. So let us put 4 here. Then you get 24 into 4. So 96 would be the right answer for this. So that is option D. So with this, we completed the second topic, that is modulus and argument of complex number was already over. This is the third topic actually. That is properties of modulus and conjugate is done. We need to start the fourth topic, that is inequalities involving modulus. So let us do this in the next lecture.